Hey everyone, in this lesson we are going to be exploring the command pattern inside of Unity. Now the command pattern is great and is very good for not just coding, performance and flexibility, but overall design of your games as well. So the command pattern at its core basically allows actions to be represented as objects. Now, this basically means we can stack up commands and execute them when needs be. Or in the case of what we're going to be creating here, we have the ability to undo commands to basically play the actions or play the inputs the player has just executed in reverse and then redo them. Okay. Now, this is great for RTS games where you might want to stack up multiple commands for a player to then execute. Turn-based games as well. Anything that requires a number of commands, a number of actions to be performed in a certain order, this is a great way of doing that. And you could even expand upon this system in order to create replay systems for your games, to create playbacks, that sort of thing. So let's look at how we can implement the command pattern inside of Unity. So what I've got here is a little example scene. So basically in the scene, I have a cube in the middle, which I've named player. And this player we are going to be moving around with the arrow keys, okay? And then down here we have an undo and a redo button. Now these two buttons are going to be what we can do to basically replay our command. So we'll move the player around with the arrow keys, and then we'll be able to click undo to basically undo that input, and then we can see the player basically then going in reverse, and then redo will allow us to then play that back. And this is just to have a look at how we can stack commands, undo them, and redo them when we wish. Now, let's get down to the scripts. So down here, I have 4 different scripts. I have command executor, iCommand, move command, and player movement. Now we're going to go through and fill each of these in. But first of all, I'm going to select our player right here, and I'm going to attach the player movement script. Now you can go ahead and create these 4 scripts right now. Attach player movement to the player. And then I'm going to create a new empty here, and I'm just going to call this one our command executor. And I am going to attach to this one the command executor script like so. Now, let's begin by creating the base class or the base interface for command. So I'm going to open up the iCommand script right here. Now, an iCommand is going to be an interface, and it is going to basically lay out 2 functions, execute and undo. So let's go ahead and create that right now. So delete the content here. We're going to remove mono behavior and replace class with interface. Now, iCommand, we are going to have 2 things. We're going to have a void execute and a void undo. Now, a command is basically going to be, well, anything. In our case, we are going to have a movement command, which is going to, when executed, move the player along a certain direction, okay? You can have other commands as well. You might have a jump command, you might have a change color command, you might have an on and off command. Anything in your game that you want to happen or have a state change, you can define as a command. That is why we are setting this up as an interface, so we can easily attach this to all sorts of different command types later on. Now, the execute function is going to be called when we want that command to play out. So, for example, if this command is for the player to move up, well, execute would move the player up. And then when we call the undo function, that would basically reverse the command, okay? So that would then move the player down, essentially. Or if you have a command to turn on a light bulb, execute would turn it on, and undo would turn it off, okay? Or revert back to its previous state. Now, what we're going to do next is move over to our move command script. Now, move command is going to be where we actually define the meat for the movement command for the player, okay? Now, this here, we're going to remove start and update, and we are going to replace the mono behavior with iCommand. Now, this script is not going to be attached to a game object, so that is why we are not using mono behavior. Rather, we are creating a new class of type iCommand. You'll see we have the red line, and that is of course because we need the execute and undo functions. Now, to easily do this, I'm going to click on iCommand here, hold down Alt, press enter, and then press enter again. And that is then going to create the 2 functions for us right here, execute and undo. Inside of here, what we're then going to do is we are going to need two properties for this command, okay? Because this command is going to need to know two things. First of all, what it is going to move, and second of all, the direction and vector it's going to be moving in. So for this, we're going to create a private player movement. Now this player movement is once again that script we created, and this here we are just going to call player movement. And then we'll create another one here. This is going to be a vector 3 for the movement. So in order for this move command to exist and run, we need to know these two things: what we are moving, and then the vector we are applying to its position. Now, since this is not going to be a mono behavior, it's not going to be a component we attach, we are going to define a constructor for this class, because when we create a new class, we want to provide it with this information. So to make the constructor, we're just going to go public move command, and we're going to be sending over two parameters. These are going to be the player movement, so player movement like so, as well as a vector 3 for the movement. Now, inside of here, we basically want to just set these variables. Now, to set a variable that has the exact same name as a parameter, we can just go this.player movement, which is referring to our variable player movement up here, and then we can just go equals player movement, okay? So here we are setting the variable player movement, this meaning this instance of the class, and then we are setting this to be the parameter, which refers to here. We can do the same thing for movement, this.movement equals movement, and there we go. Now down here in the execute and undo functions, we can't actually fill those out just yet, because we first of all need to define our player movement function, or our player movement script. So over inside player movement, what I'm going to do is I'm going to delete all of this, and I'm going to create a public void move function, okay? Now move is going to take in a vector 3 for the movement, and what we're going to do here is simply apply this to our position. So we can go transform.translate, and this is then going to take in the movement, okay? Now translate is a function which basically just applies a vector to our current position. Now back inside of move command, what we can do is go down to execute. So this is where we want to execute the move command, and basically we are just going to go player movement dot move, and we'll send over the movement variable. Now undo is basically going to do the opposite of that. Now to do this, it's fairly simple. We're just going to go player movement dot move, and we are going to be sending over negative movement, okay? So if this vector here is up, well, when we undo it, it's going to be down. If it is left, it's going to be right. If it's forward, it's going to be back. Okay, so we're basically negating that movement vector right there. So we have our I command, which is the interface for execute and undo. We have our move command, which is basically creating that command. It's taking in what we are moving as well as the vector. And then we are filling in the execute and undo functions to correctly execute that command and then undo that command when needed. Now, how can we actually go ahead and get this working? Because right now we've created these scripts, but they don't really do anything. Well, that is where the command executor script comes into play. Now, inside of command executor, we are going to delete start and update here, and we are going to create 3 new variables. The first one is going to be a serialized field because we want to access this in the inspector, and this is simply going to be our player movement, a reference to our player movement. The next 2 variables are going to be stacks. Now for this, we are going to be using the system.collections.generic library. And then down here, I'm going to go private stack of I command. And this is going to be called undo stack of new stack I command. Now, whenever we are going to execute a new command, we are going to add it to this stack here. Now, a stack is very similar to a list or a queue if you've used those before. Basically, a stack is first in, first out. So you can think of it sort of as a Pringles can or something like that. When you put something in, they sort of stack on top of one another, and then when you want to take something out, you have to take the top thing out. So basically, if we put a command in, we have to take that command out first. And this is basically how we are going to do our undo cache here. And we're going to do the exact same thing. We're going to create another one, another stack of I commands called redo stack. equals new stack of I commands. So when we are undoing stuff, we have we're going sort of back in time, you can think. So then we have the commands from our current position to our most recent that we are then stacking up here. And when we redo, we'll go through those. Now, in the next lesson, we are going to go ahead and fill out this script. We'll also look a bit more into the stack here and exactly how it works. So I'll see you all then in the next lesson. Welcome back, everyone. In this lesson, we are going to be continuing on with our command executor here. So what we're going to do now is we are going to create some functions. So first of all, we are going to have the update function. This is where we are going to be detecting our inputs. We are then going to have another function called void execute command. Now this is going to take in an I command variable here, or parameter called command. And this function is basically where we are going to establish this new command that we have created. We are going to execute it, and then we are going to add it to the undo stack right here. The next one is going to be a public void for undo command. This is going to be called when we click on the undo button in the UI, and this is basically going to cause us to begin reversing our commands in order. We are then going to, of course, have another one for redo command. And this is going to do the opposite, okay? Undo and redo. So up here inside of update, what we are going to do is we are going to check our inputs. So here we have if input.getKeyDown, and we are looking for the up arrow, so keycode dot up arrow. Then what we're going to do is we are going to call the execute command function, and we need to send over a new I command. Now, since move command is of type I command, we can simply create a new one of these, and we can then establish our player movement and movement vector in the constructor here. So here I'm simply going to go new move command, sending over our player movement, and we are then going to send over a vector. Now for this, I'm just going to go vector3 dot up. Okay, and there we go. Now we can go ahead and do the exact same thing for all three different directions. So we have down, left, and right. So I'm just going to go fill those in right now. And there we go. So we have up, down, left, and right. And I've gone ahead and changed those vectors as well. Now, let's go down to the execute command function, which is what we are calling here. So the first thing we want to do is go ahead and execute this command. So we'll go command.execute. Now, for our move command, this is basically going to move our player, okay, based on the given properties here. What we then want to do is add this command to the undo stack, okay, because if we want to eventually undo it, we need to know that it has existed. So here we are going to go undo stack dot push command. Now, push basically means it is adding it to the stack, and you can think of the stack again as sort of like if you're stacking bricks, okay? You have one on the bottom, then one on top of that, then one on top of that, then one on top of that, and push is basically adding one to that stack, okay? Push is kind of a counterintuitive name for something like that, but you get the idea. And basically what we can then do in that stack is we can then retrieve, okay, or pop out a element from that stack, which basically means we're going to get the top one. So you can sort of think we're stacking it up with bricks, and then if we want to start retrieving stuff from that stack, we have to go from the top down. So this is known as last in, first out. Okay, the last thing to be put in is going to be the first thing to be taken out. So what we also then want to do is we want to clear the redo stack, because if we are, for example, maybe undoing and executing commands, the redo stack we basically want to nullify. We want to clear it out each time. So here we're going to go redo stack dot clear. Now let's go ahead and test this out. So I'm going to hop back inside of Unity here, wait for everything to correctly compile. Okay, we have all of our scripts that we have just filled in. And also make sure once again that the command executor has the command executor script. We can then drag in our player into the property here, and on our player, make sure that the player movement script is attached. Now, if I press play, we should be able to move around with the arrow keys. Okay, and if I move around, as you can see, there we go. Now, these commands are being executed each time we click, and it is being added to the undo stack. Now, what we need to do is set it up so that when we click undo, we can see these actions being taken in reverse, and then redo when we want to re-execute them, okay? So, let's go have a look at how that can work. What we're going to do is go down to the undo command function, and in here is where we are going to basically revert back to the previous command. So here we first of all need to make sure that we do actually have stuff in our undo stack. So we'll go if undo stack.count equals 0, then we are simply going to return, okay? Otherwise, we are going to get the current command, so iCommand for the current command equals undo stack.pop. Now pop is basically going to get the top or the most recent command added to that stack. Then what we're going to do is we are going to add it to the redo stack. So here we'll go redo stack.push our current command. So then when we eventually want to redo those actions, we can easily do that by having a look at this redo stack. And then finally, we want to go current command dot undo, okay? Now, down here inside of redo, we basically want to do the opposite. So we're going to check to see, first of all, if the redo stack exists. So if redo stack dot count equals 0, then we want to return and not do anything, because otherwise, you know, we're not going to be pulling anything from anywhere. We then want to get the current command, so iCommand, this is going to be our current command equals redo stack.pop. Then we want to add it to the undo stack, so undo stack.push current command. So once again, we're basically doing the exact opposite thing here. And then of course, current command dot execute, okay? Because since we are redoing those actions, we are moving forward through time again, so we need to execute those. And there we go. That is our command executor script complete. Now, let's hop back inside of Unity and actually look at setting these buttons up. So you can go ahead and create a UI canvas and buttons if you wish, or you can maybe set this up as keyboard inputs. It's really up to you. So I'm going to go to our canvas and I'm going to select our undo button. Then in the inspector at the bottom, I'm going to go to where we have our on click event, and I'm going to add a new listener. I'm going to drag in our command executor and set the function to be command executor undo command. And redo button is basically going to do the exact same thing, but for the redo command function. Okay, there we go. Now, if I press play, you should see that I can move around just as before. So let's say we want to move to the left a little bit. So we'll move to the left here. Now, if I undo that, by clicking on undo, you can see the actions are being undone. I can then redo them, undo them, and so forth. Okay, and then we can move around again, maybe move up here a little bit, down here. We can then undo those actions, and as you can see, we are going back in time. We can then redo them again, and halfway through, I might want to move over here, but if I click redo again, you'll notice that nothing happened, and that is because we are sort of branching off from what we had before. So yeah, that is a look at the command pattern inside of Unity. It basically allows us to store inputs as commands, as objects, and then utilize them however we wish, okay? And once again, this is great for turn-based games where you want to sort of stack a number of commands for the player to execute. This can also be very good in multiplayer games, okay? Because in multiplayer games, you have all these other players sending over inputs. The server then has to determine, okay, this player wants to move here, this one wants to move here. It can be really good for latency issues, okay? If you need to revert a player back to a previous point in time, you can look at their commands and undo them, or if the player needs catching up, you can send over a chunk of commands for them to execute all within one frame. There are many use cases of the command pattern when it comes to game development, and I'm sure in the future when you create more games, you might want to create turn-based games, RTS games, multiplayer games, the command pattern is going to be very useful. Okay, so as a bit of a challenge, what I want you to do is I want you to set up a new command for scaling the player here. So let's just say when we press the S key, that is going to increase the player's scale. Okay, so set up a command for that, set up the input, and I'll be right back to see how you're done. Alright, so I hope you had a go at that challenge. First thing we want to do is create a brand new command. So just like we have a script from move command, we are going to create a new script here. And this one is going to be called scale command. Okay. We then want to go ahead and open this up inside of Visual Studio. And the first thing we're going to do is replace mono behavior with iCommand, of course. We're going to remove the start and update functions, and we are going to add in the execute and undo functions right here. Now, before we continue, let's go over to the player movement script and add in a new function for scale. So here we go, public void scale. We'll create a vector3 for the scale amount. And here basically what we're going to do is we're going to go transform dot local scale plus equals scale amount. Okay, and that then is going to add that scale onto our player's scale. Now back in the scale command function, scale command script, what we're going to do is we're going to create two variables. We're going to create a private variable of type player movement so that we can keep track of which object or which player thing that we actually want to modify, and then also another one for a vector for the scale amount. Now we need to create a constructor for this class, so we'll create a public scale command. This is of course going to take in a player movement and a scale amount of type vector3. And then inside of the body of the constructor, we can simply go this dot player movement equals player movement, and this dot scale amount equals scale amount. So basically we're doing the exact same thing as we've done with the move command. Now, down here in execute, we are going to send over, or we're going to call the scale function here that we just created. So here we'll go player movement dot scale, sending over the scale amount. And likewise, for undoing that, we are simply going to negate the scale amount. So here we'll go player movement dot scale negative scale amount. And there we go. Now finally, we need to go over to our command executor script, and this is where we are going to define the input. So here, I'm going to add a new if statement. So if input.get key down keycode.s for scale, we are going to call the execute command function. But instead of sending over a new move command, we are instead going to send over a new scale command, okay? Adding in our player movement, and for the vector, let's just go new vector3, and we'll go 0.2 and 0.2f for everything here. Okay, there we go. So that should work. That is all we need to do. Everything else is set up automatically for us. So now if we go back to our project and press play, you should see that we can then move around just as before. So you can see I can move around, and now if I press S, we'll increase in scale. I can move, scale, move over here, scale up a bunch more, move around, scale up. And if I undo this, you can see that we are undoing all of those actions, which is great, okay? So you can see how we can add simple new commands in order to really change our game here. And you can add other ones as well, maybe such as a shooting command or maybe a change color command. There are many different commands and things that you can do with this system. In this lesson, we are going to be going over how to create entities using ECS. Now, there are many ways of doing this. The easiest is by creating one in the editor, although later on we will be looking at how we can create entities inside of our scripts. So, before we start, let's first of all go over again what an entity is. Now, an entity is basically like an empty box, you could say, okay? It's basically an identifier. You give the entity a name, and with that name, we can then link different components and data to it, okay? So a good way of thinking of an entity is in a way like an empty game object. By itself, the empty game object doesn't really exist, it doesn't really do anything in our game, but when we attach components and data to it, it then becomes something more. That is essentially the same thing with ECS, okay? But it is a bit different, and we'll go over the differences in just a second. So, first of all, how do we create an entity? Well, like creating a game object, we could right click in the hierarchy, go 3D objects and create a sphere or something, but that is just going to create a traditional game object with our traditional components that we are already used to. So what we need to do is first of all create something what is known as a sub-scene, okay? This is going to be something we create here in the hierarchy. So I'm just going to right click, and then down at the bottom I'm going to go new sub-scene, create empty scene right here. We can then give it a name. I'm just going to call this one our entity sub-scene. You can really call it whatever you wish. And then as you can see, it is going to be created right here inside of our main sample scene. Now, everything that we create inside of this entity subscene, that is going to basically be initialized as an entity, and I'll show you the difference. So let's go ahead and create an entity. Now, this is basically done the same way as creating a game object. We right-click. This time, we're going to right-click on the entity subscene, and I'm going to go prefab, or not prefab, I'm going to go game object, 3D, and let's go ahead and create a cube, okay? So that's going to go ahead and create our cube object here as normal, but there's one thing you may notice, and that is down here at the bottom of our screen, we have this little preview window here that you can pull up like that called Entity Baking Preview. And as you can see here, we basically have a large list of different things, okay? Blend probe tag, chunk world render bounds, all of this stuff that you probably haven't heard of before. And these are our components that are basically attached to our cube entity right here. Now, it is probably looking a bit confusing because we also have our components here, such as mesh filter, mesh renderer, box collider that you're already used to. But these are not the ECS components. These are basically our traditional components. And down here are the components that were generated based off these three in the transform right here when we created our cube. So, what we are looking up here in our main inspector, these are not the entities that ECS is using, okay? Instead, these ones down here are, okay, this large list here. Now, how can we actually see all of these properties? Well, to do that, we need to change the way we are looking at our inspector. And to do that, we're going to go to the top right where we have this little circle here. We're going to select that, and you can see we can change the type of inspector we have. By default, it is set to authoring, which is basically the traditional way of seeing our components and everything. But we are instead going to switch it over to runtime. And runtime is going to be displaying all of our ECS components that are attached to the entity, okay? And you can see here we have a large list of them. We have local to world, which basically acts as our transform component, chunk world, render bounds, editor render data, all of these right here. Now, initially you may be thinking, okay, these are just like normal components, okay? They're basically just scripts with variables and logic that we attach, but no, it's a bit different than that. The way ECS components work is that a component, unlike a script, does not contain the logic or computational things that a script may normally have. Instead, an ECS component is merely a list of data, okay? It's merely variables, data. So everything you see here, for example, material mesh info, this entire component, all it contains is these two values, material and mesh. It doesn't contain any of the logic that would then process its information. That is done on a more abstract system script that reads this data and then modifies it, okay? So none of these components have any functions or any sort of processing going on. These are all merely components which hold data. Now, why do we do it that way? Well, this is great because unlike a traditional workflow where data is stored wherever there is space, Unity's ECS system stores similar data in chunks, essentially in memory. So for example, if we have local to world right here, this component is going to be stored alongside every other local to world component that is attached or linked to all of our other entities. Now, why is this a good thing? Well, let's just say we have a game where we want to have thousands of enemies running around on screen at once. We might have a component that keeps track, that is like an enemy component. Well, in memory, that enemy component is going to be stored alongside all of the other enemy components in a single chunk or multiple chunks that are all together in memory. So whenever our CPU wants to access those pieces of memory, it doesn't need to be looking around the place for everything else, okay? Because traditionally, when we create components and C# scripts inside of Unity and attach them, that data is stored, wherever there is space in the memory. So traditionally, if we had 1,000 enemies in our game, those enemy components would be, one point in memory, another one over here, another one over there. And when our computer wants to process that information, it would need to search, thousands of different places, jumping all over, and that would then slow down performance. Whereas with ECS, these components are all stored together in chunks right up next to each other. So when our systems want to begin modifying and reading the data, it doesn't need to go far in order to process thousands and tens of thousands of operations in a very short amount of time. And this is where the performance increase with ECS comes into play. Okay, so if we go ahead and play our scene, it's going to look normal because we're essentially just rendering a cube to our screen, but this is done through the entity component system instead of the traditional game object with script components attached, the way we're all used to. So yeah, on the surface it looks basically the same, but later on when we start, really putting it to its test, we'll really see the performance increase that we can get from ECS. So once again, we've created an entity here inside of our subscene, and inside of this entity we have a number of different components, which is basically representing data. Now, each of these components are also going to then have a system which processes that data, okay, the actual logic that is being applied. But that system logic is not stored here in the components or in the entity, okay? The entity is basically, you can think, an empty vessel which contains components, which contains data, okay? All of the logic and processing power is run by these abstract system scripts that are outside of these individual entities, okay? So for example, if we had 1,000 cubes, we are not going to have 1,000 instances of the local to world system running this code. Rather, there will be one local to world system that manages thousands of local to world components, okay? Now, in the next lesson, we are going to be looking at how we can actually begin to create a component and from there create a system that can then modify that component data to change what we see inside of our game. So thanks for watching, and I'll see you all then. Welcome back everyone. In this lesson, we are going to be going over setting up our components for our entity. Now, the first thing I'm going to do is actually go ahead and delete the cube because instead of a cube, we're going to be using a red sphere, okay? And later on, once we add in thousands of them, it's going to create a nice visual. So I'm going to go ahead and delete the cube here from our entity subscene. I'm then going to create a brand new 3D object of type sphere. This is going to be turned into an entity, of course, as you can see here with the entity baking preview. We can then rename this to be ball. And then let's also apply a nice red material to it. So down inside of the assets window, I'm going to create a brand new material right here. I'm just going to call this one red ball. And we can just attach it as normal, so we can drag it on to the object like so, and then change the color here. Alright, there we go. Now, the next step is going to be creating our component that we can then attach to our entity, because right now, as you can see in the inspector, we have all of these components here, and we want to create basically a ball data component. Now, why do we want this? Well, in the example we're creating here, we are going to have our ball moving around the screen randomly, okay? So we need to create two variables for our ball. We are going to create a speed variable and a direction variable, okay? So a vector for the direction and a float for the speed, okay? How many units per second they are going to be moving. So for this, I'm going to go and create a new script. Now this is going to be called, actually first of all, to create a monobehavior script, and this is going to be called our ball data. Now you can call this script whatever you want. There is no real restrictions over names of scripts. You can generally call them what you wish. So we are then going to open this up inside of Visual Studio. Okay, and here inside of Visual Studio, we can begin. So to start, we are not going to be having this class of type monobehavior, okay? This is not going to be attached as a component, this script. Rather, it is going to be a struct containing data. So I'm going to start by deleting void and updates, start and update, I mean, since we won't be needing those. We then want to go to the top here and add in two new libraries. The first one is going to be using Unity.entities, which is going to allow us to access all the classes and libraries related to ECS. And the second one is going to be using Unity.mathematics. Now, when it comes to the maths libraries and vectors, we are using a different library in ECS than we would with traditional Unity. In traditional Unity scripting, we would use vector3 to capture an X, Y, and Z direction or vector, whereas inside of ECS, we use something known as a float3, and we'll get into it in just a second. So first of all, we need to modify our class right here. The first thing being is that this isn't going to be a class. This is going to be a struct. So replace the keyword class with struct, and this is just going to change how this structure here is stored. Okay, a class is going to basically create one instance of that, and then we're going to reference that, whereas a struct, every time we reference a struct, it creates a new set of data, and that's just the workflow that ECS uses. And then instead of mono behavior, we are going to be implementing the iComponent data interface. Okay. And this defines this script here as a component, and now we can fill in our variables. So we're going to have two variables. We're going to have a speed and a direction. So here I'm going to create a public float called speed, okay, just as you usually would. And then we're going to create a vector for our direction. Now traditionally we would go public vector3 direction. But this is not going to work, okay, because when we are interacting with ECS components, we have to use the new mathematics library. Now, you can, of course, go online and look at the individual aspects of this, as there is quite a lot of stuff. It basically replaces all of Unity's existing mathematics libraries. So we are going to replace vector3 with float3, okay, and this is essentially the exact same thing as a vector3, okay, but each value is being stored as a float. So we have x, y, z, 3 axes, float3. And there we go. That is our ball data script here. Okay, now we need a way of actually attaching this ball data component to our ball, because right now you can see if we click on our ball and if we are in the runtime here in the inspector, you can see that we have all of our components attached to the ball, but we don't have the ball data just yet. So how do we actually attach it? Well, if we go back into our authoring inspector where we have our components, we can't simply just drag and drop this in because it's not of type mono behavior, okay? We can only attach mono behavior scripts as components. So what we need to do is create what is known as an authoring script. And an authoring script is basically a middleman. Its job is to basically attach this component to the entity. So what I'm going to do here is I'm going to create a new script called ball authoring. So we'll create this here, ball authoring. We can then open that up inside of Visual Studio. All right, so in this script, we are basically going to create a baker, which is going to bake our ball data component to the entity. So to begin, we're going to delete start and update. We are still going to keep this class as a mono behavior because we're going to attach this to the game object. And then at the top, we need to, of course, be implementing the unity.entities library and unity.mathematics, since we are going to be using that float3. Now, down here inside the class is where we are going to enter in basically the properties here that we have already created so that we can actually modify them in the inspector. So essentially, we can just copy and paste our variables and put them right there as we've done before. And now to actually bake our component and attach it to the entity itself, we need to create our custom class, which is going to do exactly that. So this class is going to look a bit like this. We're going to go private class, and I'm doing this inside of ball authoring because this class is only ever going to be used by this script, so we don't need to actually make it a public one. We're going to call this one baker, and it is going to extend from a baker class, and then we can define a type here. Now, this has to be of type authoring type, which is going to be our ball authoring script right here. So it'll extend of the ball authoring type there. And then inside of here, we need to define an override function. Now, this is going to be a public override void called bake, and it is going to have a ball authoring parameter here. And inside of this function is where we are basically going to get our entity that this script is attached to. We are then going to attach a new component of type ball data. Okay, remember this here is the component we want to attach. And we are basically going to transfer these properties that we have defined here in ball authoring over to our ball data and then attach that as a component to the entity. Now, we'll be working on that in the next lesson and seeing if it works. So thanks for watching, and I'll see you all then. Welcome back. Let's continue on with our ball authoring script. Now remember, the ball authoring script is basically acting as a middleman. This is where we can set our properties in the inspector, and then at the start of the game, we are basically running this bake function down here, which is going to first of all get the entity that this script is attached to. So it's going to get our ball entity, and then we are going to attach a brand new ball data component to that entity, okay? Because we can't simply drag and drop ball data onto the ball game object. That's just not how things really work, because we can only attach mono behaviors to game objects. So that is why we are using this mono behavior as, like I said, a middleman to then bake on the actual component itself. So down here inside of the bake function, we want to do two things. First, we want to access the entity that is basically attached to the game object this script is on. So to do that, we can simply create an entity variable here, call it entity, and this is going to be equal to get entity. So it's going to get the entity that the game object is on. Then what we can do is define the transform usage flags. Now this basically determines how the transform components are set up, and there are a number of different options. So basically, if we're setting up a management component that isn't really going to be moving around or visible in game, we might set that to be none. For example, if we're creating a game manager, an audio manager, something like that you want as an entity. But since we are creating an object that is moving around, we want to set this to be dynamic, because they are going to be updating and changing their position and scale and rotation over time. So we'll set that to be dynamic. Now the next step is going to be attaching our ball data component to this entity. And we can do that by calling the add component function. We have two parameters. We have the entity and the component. So define the entity right here. And then for the component, we want to create a new instance of the ball data struct. So here I'll go new ball data. Opening and closing squiggly bracket is where we can basically set or establish the variables. So basically what we want to do is we want to set the speed and the direction of our ball data to be the speed and direction of our ball authoring, because remember, the ball authoring script is attached to the game object, so we can modify these values there, and then here is basically where we want to pass them over to the component. So for this, we are simply going to go speed equals authoring.speed. And once again, the authoring we are accessing here is the ball authoring, which is being sent over in the bake function, okay? So it's basically this right here. And then we want to then go direction equals authoring.direction. And there we go. That is everything we need to do for our ball authoring script right here. We have our variables that we are basically having to set up in the inspector and then transfer over to the baked component. And down here in our bake class, and this is where we are actually baking or attaching the ECS component to the entity itself. So we can save that, go back into the editor, and actually look at how we can then set this up. So now that we have a script that is of type mono behavior, this means we can actually attach it to the game object itself. So if I select the ball right here, and if I then drag on ball authoring, like so, you can see it attaches the ball authoring component here. We can then define some parameters, maybe direction, we want to set Y to be 1, speed, we might set that to be 2, okay, so 2 units per second going up. Now, if we switch over to our runtime inspector, you can see here that if we look through, we have a new component called ball data, and you can see the speed is 2 and the direction is 1 on Y. So whenever we go ahead and we modify the actual component attached, the ball authoring component, so speed, we might make that 1.5. You can see if we go to runtime, those changes will be applied to the ECS component right here, okay, which is great. So that is how we can attach components to our entities. Now, this entity has the ball data, but it doesn't actually have any of the logic behind it, okay? It knows its speed, it knows its direction, but how do we actually apply that? Now, what we don't do is go into the ball data struct and begin creating functions here, okay? Because remember, when it comes to the system side of things, none of the logic or the processing is done on the component or on the entity, okay? So ball authoring and ball data are pretty much complete. If we want to add more variables, then we simply do that. But if we want to actually start reading and modifying this data, we have to do that in a separate script, which is going to act as the system. And the system is not attached to this ball game object, ball entity, or ball data component. The ball system is going to be its own exclusive script, which is going to basically run or process logic for every single instance of ball data in our game. So in the next lesson, we'll explore how to set that up. Hey everyone, in this lesson, we are going to be looking at the third element of ECS, which is system, okay? And the system is where we actually define the logic for our components on our entities. So we have our entity, which is basically the empty vessel, which links to a number of different components, as we can see here in the inspector. And each of these components references a number of different pieces of data or variables, but they don't actually do anything. These components themselves, all they know is that they have this information. They don't know what they want to do with it or what it is for. That is where these systems come into play. And the systems are basically the scripts which look at these components. It can then modify that data and then read it and then do stuff based on whatever we wish. Okay. So in our case, we are going to create a ball system, which is going to read our ball data speed and direction, and then modify that with its transform here along that direction at that speed. So to begin, we are going to create a brand new C# script called ball system. Now, when it comes to systems, since these aren't going to be specific to any one game object like traditional components, we aren't going to be attaching this to a game object. In fact, we're going to turn this into a struct, okay? So this script is going to exist in the code base, and at runtime, it is going to identify all of the entities that have a ball data component and then run this code on them, okay? So let's open up ball system right here. And there are a few things we need to do. First of all, we need to add in our libraries. So we are going to be using unity.entities. We are also going to be using unity.mathematics to access, like I said, the float3 vectors. And then we also need to be using unity.transforms. And this is going to allow us to modify transform positions and stuff like that. Now, the next thing we need to do is go down to our class, and we first of all want to change this class into a partial struct, okay, is because we are using what is known as an unmanaged system, okay. Now, there are also managed systems, and using one or the other is probably going to be something that you could debate, but generally using the unmanaged system is going to be the best, as this allows us to use the jobs and burst compile systems, allowing for very fast code and very fast games. So instead of mono behavior, we are instead going to implement the iSystem interface, which is going to turn this into an unmanaged system. Now, the main difference is that with a managed system, for example, we would be able to utilize and store and use any sort of data type, whereas with an unmanaged system that we are using, we are limited to the basic stuff like floats, ints, bools, float3s, those sort of things. But for 99% of the stuff you're going to make with ECS, that's going to be fine. And the benefits of having a very fast runtime and compilation and being able to use multi-threading, assigning jobs, is going to outweigh the negatives greatly. Okay, so this is what we're going to stick to in this course. Now, what we need to do is we are first of all going to create a function called onCreate. So I'm going to create a public void called onCreate. And in here, we're going to send over a parameter, and this is going to be a reference to the system state variable, which we'll just call state. Now, onCreate is going to be called at the start of the game when the system is first initialized, okay? And what we are going to do here is basically tell this system to only run if it finds a component of type ball data, because if there are no ball data components inside of our game, well, we don't want to be running the update function. So here we are simply going to go state.require for update ball data, okay? So this is just general practice. We're not really going to run into any errors if we don't have this, but later on when you might have certain components that don't come in until later on in the game, you can run into some errors there. So basically what we are doing is we are saying that the following update function should only run if there are existing ball data components in our scene, okay? Now what we can do is create the meat of the system, which is going to be our onUpdate function. So we're going to create a public void called onUpdate, which is going to have a reference to the system state called state. And in here is where we are basically going to be creating our jobs that we want our balls to do. Now, what is a job? Well, essentially a job is a process that we can then create and then queue to be run on the processor, okay, on the CPU. Now, why would we do this over just running the code when we get to it? Well, because when that happens, we are sort of cramming all of the code into one single thread. So it has to go line by line, operation by operation. And if we have thousands of these operations that we want to run, for example, if we have thousands of balls in our scene, well, that's going to slow us down. So what creating jobs does is this essentially allows us to implement multiple jobs, multiple processes to run at the exact same time using the multiple threads on our CPUs, okay? Because nowadays, most CPUs have, at least 4 cores, okay? At least 4 threads that it can run. So what jobs does is it schedules jobs to be run on different parts of the CPU. So instead of having to go through 1,000, ball update functions every single frame, step by step, instead, we can divide that up into maybe, 10 different chunks that are all running at the same time. So that's the benefit of jobs, and that is essentially what allows us to use multi-threading here inside of Unity to get some insane performance increases. Okay, so how do we actually do this? Well, first of all, we have to define a job. Now, to do that, I'm going to go down here and I am going to create a brand new class. Now this class is going to be inside of our ball system because this is the only place it's ever going to be used. And we are going to create this and it's going to be called a public partial struct called ball job. Okay. And this is going to extend from iJob entity. Now inside this struct, this is basically where we are going to be running the code for the ball. So for this, we're going to create a public void called execute, and this is going to have 2 parameters. We are going to be sending over the ball data, okay? So we'll be sending over the ball data component, and we also want to be sending over our local transform component. So ref local transform, and we'll just call this one our transform. Now, these parameters here are totally custom. We can define whatever parameters we want, and this is essentially the components that we want to read and modify, okay? So, of course, we want to be reading and modifying our ball data because this contains our speed and our direction, and our local transform component, which we saw in that big list of entity components, this is going to contain our position that we are then wanting to update. And then there's going to be a local transform system out there, which is then going to apply that and rendering and so on and so forth. So all we want to do is modify this component here. Now, when we are running this, okay, this is essentially going to be called every single frame, and we are going to be wanting to move our ball. Now, generally in Unity, when you're moving something in the update function, you want to be utilizing the delta time variable. Whereas here, since we aren't really running in the update function and we don't really, it's sort of disconnected, we kind of want to send over some data as well. Now, we can send some data over with our job because the job isn't going to be able to access the delta time from inside here. So we need to sort of cache that beforehand. So up here inside of the struct, I'm just going to define some variables. So we can go public and then float for delta time. And then down here in the execute function, we can then access this delta time. Now, how do we actually go ahead and create a job? How do we establish all of this and let it run? Well, we do that here in the onUpdate function. And in the next lesson, we are going to be implementing that. So thanks for watching, and I'll see you all then. Alright, so welcome back. Now what we're going to do is inside of our onUpdate function, this is essentially where we are going to schedule a new job and then apply that. So here's what we need to do. Inside of onUpdate, we are going to create a ball job. So we'll go ball job, call it job, equals new ball job. And then inside of the squiggly brackets is where we can define our delta time. So for this, what we're going to do is we're just going to go delta time equals. Now, traditionally, we'll just go time.delta time, but that's not going to work for us because inside of ECS, we have to use its mathematics libraries and system libraries. So for us, we're going to go system API dot time dot delta time, okay? And that is how we can access the delta time. And there we go. Then what we need to do is we need to schedule this job. So we basically need to go, okay, we have this job and we want to run it. And if there is an available thread, it will take it up and it will run the job. So here we can then just go job.schedule parallel, okay? And that is what we need to do for the onUpdate function. Now down here inside of the ball job struct, inside of the execute function, this is where we are going to be running basically the update code, okay? Think of this as our onUpdate function. So what we are going to do here is we are basically going to move our ball based on its direction, okay? So what we're going to do is we're going to create a line like this. We're going to go transform, which is accessing our local transform component, which defines our position, rotation, scale. We are going to equal this to transform.translate. Now transform.translate, this is something we have in Unity already. It basically applies a vector to the position. So in here, all we're going to do is we are going to get our ball direction that we defined in our ball data component. So here we'll go ball.direction and then multiply that by the ball.speed and then multiply that by the delta time, okay? And there we go. So that is how we can modify our speed, because essentially what translate does is typically in Unity this would just be a function, a void function, but here it is a function that returns the local transform component. So we are basically assigning the transform component to be this new modified version with this translation applied. And that is all we need to do. So we can save that. We can then go back inside of the editor. And since the system script, like I mentioned before, is not, based on one specific instance, we don't have to attach this to anything else, okay? This exists in the code base. And all we need to do now is make sure that we have our ball data component attached, make sure all the properties are assigned as we wish, and then we can simply press play. Now, as you can see, the ball is now moving up. And you can see here in our local to world component, or in our local transform component, we can see that the Y position is being modified. So this is essentially the component that we are accessing to translate, and we are reading the data from ball data here. So there we go. Now, we could also go ahead and duplicate our ball multiple times, so we can create multiple different ones here. And you can see that they are all going to do the exact same thing because they are all utilizing the ball system and they are all running the exact same code. Now, with this, we might want to start adding in some variation. And in the next lesson, we are going to be exploring a bit more into the new Unity mathematics library, as well as looking at how we can start applying some randomness to the direction we are moving in. So thanks for watching, and I'll see you all then in the next lesson. Hey everyone, in this lesson we are going to be exploring optimization methods with real-time lighting inside of Unity. So this scene right here I have with dozens and dozens, probably even 100 or so real-time lights. Now the performance is okay, but with a scene this small with very simple low poly meshes, we should be getting better performance than we are right here. Now, what are we actually doing in this scene? Well, inside of the scene, we have a number of different lights, okay? And if you notice, all of these lights here are casting shadows. They're different colors, different sizes. These street lights here have two different light sources, spotlights, point lights, all casting shadows. And generally, that is something you want to avoid, okay? Because right now, if you'll notice here, inside of our game view, everything looks fairly fine, but if you look closer, you'll notice that some of these lights are not rendering at all, okay? Each of these blocks have like a green light here, whereas up here there is no green light. These street lights over here aren't showing lights either, so what is going on? Now, the reason why that's happening is because the default rendering path for Unity has a cap on how many real-time lights you can have visible at one time. And in fact, if I get my main camera here, and if I go ahead and let's just say I drag it forward like this, you can see that the lights that are closer to the camera are going to begin popping in, while those further away are going to basically disappear. And that is just Unity's way of making it so that we are not rendering hundreds of real-time lights at once and end up crashing our game. So, what are the ways that we can optimize this? Well, first of all, if we want a straight up doubling of our FPS, we can start by turning off shadows. Okay, shadows are one of the most expensive things that you can really have in a game because they require multiple rendering passes. They've got to be calculated. You've got to generate shadow maps and all of that, and it can be quite taxing on your system. So we could go ahead and go through and disable shadows on all of our lights. Or what I would recommend is if you are having a game where you have a player walking around, probably have shadows on for lights that are closer to them. But for lights that are up on these buildings here for more accented visuals, we can turn those off. But just for an example, I'm going to go ahead and turn off all of our shadows here. So if I hop into game view, what I'm going to do is I'm going to go over to where I have my URP render pipeline asset right here. And what I'm going to do is down here in the lighting section, I'm simply going to disable cast shadows on my additional lights. Now you can see if it's on, if it's off, there's a small difference. And if you are creating a sort of top-down isometric game like this, where you have a very distant camera from your game world, then really you probably don't need shadows at all. Your main light, which acts as a sun, you could probably still have that on, but for everything else, I would recommend having no shadows on them, as the difference is not even that noticeable. And honestly, a nice little hack is if you have screen space ambient occlusion enabled, that in many ways can sort of simulate shadows a bit. As you can see when I turn it on and off, I'm not too sure how it's going to appear in the video, but it does give sort of connecting edges a bit of that darkness to sort of simulate, I guess, like depth and shadows and stuff like that. So SSAO is a way of sort of faking shadows in a way. It's not exactly the same thing, but it can sort of simulate that at a distance. But yeah. So we're going to turn off shadows here, and if I press play, we can see that our performance is going to be quite a bit improved. So what I'm going to do is actually I'm going to enable them while we're playing the game. So you can see right now, shadows off, we're at about 200 FPS. If I turn them on, we're going to jump down to about 100. So you can see that shadows are basically doubling or halving our performance if they are on compared to if they are off. And if we have a game like this, where we're at a distance, doubling our FPS for a very minor reduction in visual quality, I think is 100% worth it. Now, we have one more issue with our real-time lighting, and that is the fact that the lights in the background here are not actually on, okay? They're not visible. Now, that is generally something you want. You probably don't want to have thousands of real-time lights appearing at the same time, but if you do, then you can choose to go down an alternate rendering path that Unity provides. So let's have a look at the different rendering paths that Unity has. So what we're going to do is we're going to go to our renderer asset right here, our universal render data. If you're using HDRP, then you can find your respective one of these. But if we go into the inspector now, you'll see here we have rendering path, and this basically determines how these objects are rendered to our screen. And the rendering path is really, it has a few minor things it changes in terms of like how it renders transparency and shadows and stuff like that. I recommend you read more up on it, as there are some very fine details between them. So the options we have here in UDRP is forward, forward plus, and deferred. If you're using the built-in version of Unity, then you'll be on the forward rendering path, and you'll actually have to go to a different window in order to modify this. I believe you have to go to your graphics settings inside of the project settings window. And we can actually switch between these live. So if I switch over to forward, you'll see that all of a sudden we have even less lights. Okay, none of these buildings here have their window lights on, and that is because the forward rendering path has an even greater limitation on how many real-time lights it can show at once. If we swap back over to forward plus, you'll see that we are rendering much more. And generally in the newer versions of Unity, I think forward plus is the way to go, as overall it has a pretty good balance between forward and deferred. Now, what deferred allows us to do is it allows us to basically render as many real-time lights as we want. Okay, so we don't have a hard limit. if we wanted to have thousands of real-time lights in our scene, it is going to render every single one of those. Now, the downside is that there is a bit of an overhead. So if, for example, you have quite a small scene with a bunch of lights, you're going to actually notice your FPS drop a bit, okay? And in fact, if we press play, we might in fact see that right here, okay? And yet you can see actually our frames are kind of dropping a bit. Even if we go ahead and disable the shadows, we are still not reaching that 200 FPS limit. Now, the reason why is because with deferred, even though it allows an unlimited number of lights, there is sort of a point where if you don't have enough lights, or if you're not utilizing it to its fullest potential, then you're not going to get the benefits, okay? I recommend you do more research on how these rendering paths differ, as there are many different ways. For example, on mobile games, deferred is not really a standard. You really want to stick to forward if you're on mobile devices, but if you're on PC and you're really only targeting higher end devices, then deferred could be a great option, okay? So that is a look at the different rendering paths as well as real-time lighting. Now, if you're having a normal scene like this, where you have lights and it's static, then I'd honestly recommend baking most of these lights here, because if you are having a static level that is set at night, you do not need all of these real-time lighting. And in fact, if it's baked, you can get much more high fidelity in your lights. You can get nice light bounces. You can get just overall better visuals with light baking. Whereas if you're having a scene that is perhaps dynamic, maybe you want a day-night cycle, then baking lighting for that is a more difficult thing. So in that case, I would recommend using real-time lights. But do be aware that lighting inside of game engines is one of the most taxing things on your performance, especially if you are casting shadows. Now, in UDRP, something we can also do is change the shadow resolution. So, for example, if we go over into here, let's go ahead and select this yellow light right here. Now, if we go over to the inspector, down where we have our shadows, you'll notice that we have a resolution. Now, this can change. So right now I have it set to low, because otherwise we will have errors popping up here, basically telling us that we have either too many lights or our shadow maps are going over the texture limit, okay? But if I switch this over to high, you'll notice that our shadows are far more crisp now. And your initial reaction is probably to make every single light in your game emit shadows that are of a high resolution, which, for things that are closer to the ground and closer to where the player will be walking around, that's probably a good idea. But generally, if we have a light, for example, this blue one here, first of all, this probably doesn't even need to be a shadow caster, so we could actually just turn off shadows for this one, and you wouldn't even notice a difference. But for example, in the street here, where we have all of these lights, if, for example, you're creating a racing game, you don't need to have hard shadows, okay? Or you don't need to have crisp shadows. You can have the most basic shadows, or perhaps even none at all, okay? So it really depends on what sort of game you're making. But those are just a few examples of how to optimize that. So thanks for watching. Hey everyone, in this lesson, we are going to be exploring baked lighting inside of Unity. Now, one of the alternatives to having real-time lighting in your scene is to have what is known as baked lighting. Now, baked lighting is basically where we run all of the lighting calculations beforehand. So when it is running on another device as an executable, the lighting is not being calculated, okay? Because we are going to pre-calculate the lighting on our machine so that, for example, if you published a mobile, they will not be wasting processing time trying to generate the lights and the shadows and that sort of stuff. So, baked lighting is very powerful in that way. And one other benefit that baked lighting gives us is much higher fidelity. And by that, I mean baked lighting allows us to have light bounces and indirect lighting. So for example, you can see we have this here, for example. Okay, we have this red light, it's shining down onto the ground and it's making the ground red, as you would expect. Well, in real life, light bounces around. So in real life, this light would bounce, hit the floor, hit up underneath this table, underneath this awning here. Whereas right now, it does not do that, because real-time lighting inside of Unity is only direct lighting, meaning it is only going to light the surfaces it directly hits. And that is, of course, because real-time indirect lighting is very expensive. It is possible with ray tracing, but that is an entirely other aspect of Unity graphics that we're not really going to look at in this course. But yeah, essentially, baked lighting allows us to calculate the indirect light bounces. So we could then have a bit of red underneath the table as the light would bounce up off the floor and hit the bottom of the table here, which is pretty great. If you want to have higher quality visuals, light baking is a great option. Now, the downsides of baked lighting is that since we are calculating all of this data beforehand, that is going to take up file space. Now, depending on how big your scene is, how many lights you are using, the quality that you want from it, it can get quite large. Some scenes could be a gigabyte or so in light mapping data, which if file size is an issue for you, then I would recommend not light baking. But if you're able to sacrifice, a few hundred megabytes, maybe even a gigabyte for your light mapping data, then it is a great option to explore. And there are also many ways of reducing the file size and sort of balancing it between quality as well as performance in that way. And another thing is that since we are also saving these as textures that are going to be applied to our scene, it is going to take up space in memory as well. But it's not that much, and generally the performance should be actually improving upon having baked lighting. So let's have a look at how we can set this up. What I'm going to do is I'm going to go first of all and set up our scene to basically allow for baked lighting. Now there are two things we need to do. If we want an object to be included in the baked lighting, we first of all need to make it static. The reason why is because a texture is essentially going to be applied over the static objects that is going to store the lighting data. And if we have a dynamic object that's moving around our scene, we don't want to bake lighting data onto that. Otherwise, it'd be very weird to see a blotch of shadow on it, and as it rotates and spins around, it sticks to it, okay? So I'm going to begin by making every object in my scene here static. So I'll select this parent object, which contains all of these models. I'm going to go to the top right corner of our inspector and enable static, okay? And there we go. Now the next step is going to be setting it up so that our lights are also going to be included in the bake. So what I want you to do is go through all of your lights in the scene and do this. We're going to select our light. Then over in the inspector, we want to go down to where we have our light mode. Now by default, it should be on real time. And we have three options. We have mixed and baked. Now, baked means it is only going to bake this lighting, okay? So when we bake it, it's going to calculate its light rays, its bounces, and all of that. Mixed is sort of a mix between real-time and baked, meaning it is going to be included in the bake, but all dynamic objects are also going to get that real-time lighting. Now, for things like these windows here, it's probably fine to just set this to be baked, whereas if you have a sun and you want it to cast shadows on the player as they move around, something like that I would recommend switching over to real time, as you might want those baked shadows and light bounces, but also you want to actually have shadows that move with the player and perhaps other objects that are also moving around in your scene. So go through, switch all your lights over to baked or mixed, and I'll be right back. Okay, so I've gone ahead and changed all of my lights over to baked now. Now let's have a look at how I can actually begin setting up our baked lighting. So what I'm going to do is I'm going to go over to the lighting window. You can get that by just going window, then down to rendering, lighting. And in here, we want to go over to the Scene tab. Now in the Scene tab, we want to go down to where we have our lighting settings, and we want to create a brand new lighting settings asset, okay? This is just going to contain all of the settings here, so that if we want to basically copy and paste them into another scene, we can simply just use the same file. Now, down here, we have a lot of options. And when it comes to light baking, it can be quite overwhelming with how many different options and toggles and values there are to change. But generally, the default settings here should be good, although it is really going to depend on what type of scene you're making, how big it is it indoor, is it outdoor, how many lights you have. So this is really just going to be room for experimentation, and in many cases there is not one fixed list of settings that you should apply, okay? Again, it's going to really depend on what sort of environment you want to bake. Now, what we're going to do is we're going to skip over real-time lighting, skip over mixed lighting, as these generally you're not going to be changing, and instead we're going to go down to the light mapping settings. Now, here in light mapping settings, we first of all have to choose what type of light mapper we are going to use, and there are two different ones. We have progressive CPU and progressive GPU. This is basically going to determine how the lighting is going to be generated. Is it going to be generated on your graphics card or on your processor? Now, if you have a pretty good graphics card, I would recommend switching over to progressive GPU, although there are certain limitations and differences between them. You can do further research on those if you wish, but generally, if you have a pretty good GPU, I recommend switching over to progressive GPU here, okay? Now, down here, we begin with these three different sliders, and these are our samples, okay? And this is basically going to determine how long it's going to take to generate our light map, as well as the quality that we are going to get. So, direct samples is basically going to determine the resolution or the amount of data that each light is going to produce for direct lighting, okay? Direct lighting is basically where a light emits onto a surface. So this light right here we are seeing on this wall here is direct lighting. And the higher the direct samples are, the higher quality that lighting is going to appear. Indirect lighting, for indirect samples right here, is going to be the lighting, like I mentioned before, that is bounced and sort of bounced off from one surface to another, okay? Now that is a pretty high number just because when one light bounces, it can bounce in all sorts of directions, okay? So that's why this is fairly high. And then environment samples basically determines the amount of lighting data it is going to get from the skybox, essentially, okay? From the surrounding environment. Now, we can go ahead and start modifying these values. Now, by default, this is what they look like. If you have a indoor scene, you probably want more indirect samples because you can have light bouncing off walls, ceilings, floors, etc. Whereas outside, you kind of got floors, maybe a couple walls, but mainly an open sky. So in fact, we can reduce our indirect samples a little bit here if we wish. Direct samples, we'll probably just keep that at 32. And environment samples, since we are working with a sort of nighttime scene here, I'm actually going to go ahead and bring that down quite a bit, just because we don't need that. Whereas if you're working in an outdoor scene with a sunny sky, maybe clouds, something like that, I recommend keeping that up at its default value. Max bounces down here is going to determine the maximum amount of bounces a light ray can do. Generally, we just want to stick that to be 2, one bounce here, hitting the floor, another bounce up here, and then another bounce down here, hitting the floor again. That's enough generally for most scenes, although if you have perhaps a very small environment where you want the highest quality possible and you don't have that many lights, then more light bounces could be an option. Now, in the next lesson, we are going to continue to go over these settings and then begin generating our lighting. So thanks for watching, and I'll see you all then. Welcome back, everyone. In this lesson, we are going to be continuing on with looking at our light map settings, and then we're going to begin baking our lighting. So let's now go and look at what light map resolution is. This is basically going to determine how many texels per unit we are going to have. Now, a texel per unit basically means, in Unity, for example, we have meters or units, okay? So basically 1 meter is probably going to be the length of this table right here. And this basically determines what resolution, okay? Think of it as pixels. So if we divide this up into 40 different sections, that's essentially going to be the lighting resolution, okay? If it is lower, we're going to have much more blotchy looking lights and shadows. The higher this is, the much crisper the lighting and shadows are going to be, but of course, the longer it's going to take and the bigger the file size is going to be. Now for us, I reckon we just keep that at about 40. In fact, since we are having a outdoor environment and the camera is fairly far away, we could actually probably bring that down to about 30, okay? Light map padding, this basically determines how many texels is going to be separated between the baked light maps on the texture. We'll just keep this at 2. The max light map size is basically going to be the size of the individual light map textures. This is by default just set at 1024, which we'll keep. A fixed light map size, we're just going to keep that disabled. We're going to keep most of these settings as they are. Light map compression basically determines how much compression is going to be applied to these textures, okay? Now, when it comes to compression, if you set this to none, that means it's going to have all the raw pixel data in there. It's going to look the best, but it's going to be a large file size. Setting this to high quality means that the file size is going to be, it's going to slightly be reduced, but it is going to have very little artifacting. Whereas if you want the most compressed and the smallest file size, we can switch this to low quality, which is going to reduce our file size, but we're going to have lots of artifacting in our shadows and in our lighting. So I'm just going to switch that over to high quality for now. Ambient occlusion. With the render pipeline I'm on right now, I actually already have SSAO enabled, but you can actually build that into the light map itself, which is pretty handy here. And then all these other settings here, we're just going to keep as they are. Now, what we're going to do is simply go down to the bottom here, and we are going to click Generate Lighting. Okay, now depending on the size of your scene, this could take a couple minutes, it could take tens of minutes, it could take an hour, a couple hours, it really depends. So I recommend we just let this run for a bit. If you want more information about how this is going, we can click down here where it says Global Illumination, and that is going to open up the background tasks window, okay, so we can see it going up. So basically, let your scene bake, and I'll be right back when it's complete. Alright, and we are done. So, at a first glance, the scene may look very similar, but if we start looking at it a bit closer, you'll notice that the lighting is actually improved quite a bit. So, we got our red direct lighting on the wall here like before, on the umbrella, on the table, but if we look underneath, you can see here we actually have the indirect lighting applied, okay? No longer is it just black. We now have the lighting bouncing off the floor and then up into the table here. And in fact, this shadow here has a tinge of red as well, so it bounced back down onto the shadow here. Same thing for under the umbrella. Even the table here, which is in shadow, is slightly more red due to the fact that the light is bouncing around. And if we look around our scene here, you can notice that it looks okay. We got the lighting here working fine with the bouncing, it looks great. But when you start looking over here, for example, we have very small areas where the light is bouncing. It can, sort of show its flaws, okay? So here, for example, where we have the sort of shadowed area, that doesn't look the best. Over here where we have the lights blending into one another, that also is, not looking the best here. And that is mainly due to the settings we have done here, okay? It didn't take me that long to actually generate this. So what I'm going to do is I'm going to basically try and generate this again, but with higher quality settings. So what am I going to do? Well, I'm going to go ahead and increase the direct samples a little bit. I'm going to increase the indirect samples. I'm going to bring that up to about 512. Environment samples, we can bring that up a little bit as well. It's not going to be too important. Max bounces, I'm going to set to 3, so we have even more light bounces going on. Light map resolution, I'm going to bring that up to about 60. Light map size, I'm going to set this to be 2048, just so we have higher resolution textures as well. Okay, so this is probably going to increase the performance, or not the performance, but increase the file size by quite a bit. So let's generate this and see how better it looks. Okay, and there we go. Now, the file size is about 200 megabytes. Down here we can see 213 megabytes. And the quality has improved a bit. I am noticing that the shadows are crisper, first of all, since we have an increased resolution. But we're still getting this artifacting over here. Now, I think this somewhat has to do with the fact that this model here is basically just a thin plane, which could be causing these issues. So do keep that in mind. But yeah, everything else, it looks fairly nice. The shadows, like I mentioned, are pretty crisp. Now, if we go out here, you'll notice that everything, again, looks fairly nice. One thing you may also notice with this, especially in like nighttime scenes, is that you will get these weird artifactings on your meshes here, okay, that are catching a bit of the stray lights. Now, this can be solved by increasing the samples, increasing the light map resolution, maybe even the light map padding, as well as some of the light could leak over from other textures. But something else that you may also be running into, an issue, is the fact that your lighting looks absolutely nothing as it should, okay? You might have shadows streaking up your walls, lights going off on weird angles. And that can be due to the light map UVs not being correctly set up on your model. So to fix this, you want to go over to your models, select all of the models that you want to basically fix, so essentially all of them, I'd say. Then go over to model in the inspector, and then down here at the bottom, you want to enable generate light map UVs, okay? And then click apply. This is basically just going to make it so that the UVs on your models are going to basically fit into the standard Unity has for generating UVs, okay? As if you're creating your own models in Blender, for example, they can end up looking quite odd when you start generating your lighting, okay? So do be aware, if you are having issues with that, simply enable generate light map UVs, generate it again, and it should be looking normal. Okay, so that is a look at baked lighting inside of Unity, and if we go ahead and press play, we can look at our performance, which should be far improved from if we're using just traditional directional lights, and as you can see, our FPS is pretty high. So yeah, thank you for watching. Hey everyone, in this lesson we are going to have an introductory look at GitHub and why you would use it as a Unity developer. So first of all, there are two main aspects or systems that we need to cover. The first one is going to be Git and the second one is going to be GitHub. Okay, these are two different things, but at the same time they're kind of the same in many ways. So let's first of all go over what is Git. Well, Git basically is an open source version control system that tracks changes in files. Okay, so this basically allows you to push changes that you have made to your Unity project to basically this repository, and then you can also pull changes if you are, for example, an artist and you want to work on the project. You can push your changes. You might have other artists working on it. You might have other developers writing code. It's basically a great way to collaborate on a single Unity project without having to, drag the files over to Google Drive and download them or put them on a USB stick. You can use Git, which is a great way of managing all of the changes and making sure that they merge correctly together. Now, what is a GitHub? Well, GitHub is a web-based Git repository, okay? It is pretty much a website or a cloud service that utilizes Git, but the great thing about GitHub is this means that we do not need to install Git or any other software onto our computer, and we can access our files from anywhere with an internet connection. Okay, GitHub is very popular. Generally, when you're making games, and you want some sort of version control, you'll generally use some form of Git, and in many cases, you'll be using GitHub, okay? And GitHub, like I said, it just makes it a lot easier to share your files around and have different collaborators contribute to the project. Now, how does it all work? Well, there are 5 main aspects that we are going to cover. They are repository, collaborator, commit, push, and pull. Now, let's look at each of these and see what they are and how they actually help build up this version control system. So, first one is repository. Now, this is basically where we store our Unity project, the scripts, the textures, the scenes, materials, etc. Okay, all of our folders. Now, with Unity, we have our folder for our project, and inside of that, all of our files. Now, if, for example, we wanted to have someone else contribute to that project, we could, put it on a USB stick or put it on Google Drive and hand it over that way. But a repository in GitHub terms is basically like a file explorer in the cloud that we can then add files to, modify those files, delete files, etc. Now, a collaborator, these are the people who are contributing to the repository or the repo, okay? So if you have a small team of 3 people, each of those would be collaborators, and they would all be able to contribute and access the repo, okay? The next thing we need to look at is commit. Now, whenever we have made changes to the project, let's just say we have modified a script, we've changed the scene around a little bit, those changes are going to be applied to our local project, so the project we have stored on our computer, and then all of those changes are going to basically be recognized by Git, and it will then keep track of those. And then when we want to apply those changes to the repo, we will do something what is known as pushing the changes, okay? So this basically gets our commit, which is basically a log of all of the changes that have been made to files, all of the files that have been added, all the files that have been deleted, and it will then apply those changes to the main repo in the cloud. So, and then if someone else comes along, they want to see what changes we've made, they might want to modify them a little bit themselves, then they can do what is known as a pull request, which is basically where they are getting the repo from the cloud, they are pulling it, and they are basically applying it to their local project. Okay, so for example, like I said before, with the script changes, let's just say you have two script writers, two programmers. One of them makes a change, they push that change to the repo. Someone else then wants to, maybe modify that script a bit as well. Well, what they can do is they can pull that change, that file, those changes to that file will be applied on their local machine. They can then apply those changes, commit those changes, push them to the repo, and then you can sort of see how everyone is contributing, pushing and pulling in a workflow similar to this. So you have your local project, whenever you make changes, that gets applied to the commit, and then when we push that commit, those changes get applied to the main GitHub repo. And then on a new local machine, if we are just joining the project or if we want to be updated to the current version, we can then pull those changes from GitHub. Okay, so this is the basic system and how it works. Now, in the next lesson, we are going to be looking at how we can start creating a brand new repo on GitHub. Hey everyone, in this lesson, we are going to be creating a new account on GitHub and setting everything up to create a new repo that we can then use for our Unity project. So to begin, I am going to go to github.com right here, and this is the website. Now to sign up, we're simply going to go to the top right corner of the screen and select the sign up button right here. This is going to bring us over to the sign up page where basically we are then going to follow through with these instructions in order to set up our account. Okay, and once you have successfully signed up, you should then be taken to the sign in page where you simply enter in your username or email and password and click sign in. And then finally, you should find yourself here on the GitHub dashboard. Now, in the next lesson, we are going to be looking at how we can create a brand new repository that is centered around a Unity project. So thanks for watching, and I'll see you all then in the next lesson. Welcome back, everyone. In this lesson, we are going to be looking at how to create a new GitHub repository for a Unity project. So here I am on my GitHub dashboard, and what I'm going to do is simply click on the green Create Repository button here on the left-hand side. There's also one down here, and there's also one if you click on your top right corner here on your name, you can go down to your repositories and create one there. But we're just going to click on the green button right here, and that is going to bring us over to the Create a New Repository window. Now, here, what we want to do is, first of all, give our repository a name. This has to be a unique name for your account. I'm just going to call this one my first Unity project. And there we go. You can give it a description if you wish. So if you're working with multiple different collaborators, or if this is going to be a public repo, then I recommend that. But if it's just going to be a private repository that you are using to back up your projects, then it's not necessary. Now, the second option down here is a fairly important one. You have to decide whether or not you want your repo to be public or private. Public means that anybody is going to have access to your repo, not just to view it, but to download the files as well. So if you're working on a game that is something, you might be working with a team or a group of people, I would recommend switching over to private. The only time I would recommend having this as public is if you are creating a resource or tools that you want people to be able to use, or if you're creating some open source software that you want to be used by the public, okay? Otherwise, if it's a personal project or a project you're working on in a team, I'd recommend switching it over to private. You can also then choose to add a README file, which is basically just a text document that can contain information about your project. Now, this is going to be useful if it is public, but if it's a private project, then it's not that necessary. Now, down here is probably the most important thing that we set up specifically for a Unity project, and that is the git ignore file. Now, what a git ignore file is it basically lists out all of the different directories, subdirectories, and file extensions that it is not going to include when changes are committed. Now, why do we want this? Well, with Unity, there is a lot of fluff, I guess you could say, in its file system. For example, the entire library folder is generally specific to your computer and all of the preferences and settings you have set up there, and it can contain quite a large amount of files and really increase the size of your project. Because with this, we only want to be sending over and committing the files specifically that we have changed. So if we are modifying, for example, a player controller script, and that is all we do, then that is the only thing we want to be pushing to the repo, okay? We don't want to be pushing all of our cached files, all of our metadata files. That is just pointless information we are sending to the repo and increasing the file size, okay? So what a git ignore does is it is going to basically look at all of the files we are committing, and it is going to filter out all of the ones that are included in the git ignore. Now, you may be thinking, okay, well, I don't really know exactly all the different subdirectories and file extensions that I got to leave out when it comes to Unity, and that doesn't matter because GitHub has a built-in git ignore for many different pieces of software you can see here. So I'm simply going to search for Unity and select it there. And there we go. Now, next up is a license. Now, again, if this is a private project, it's not that necessary, but if it is a public project and you want to specify explicitly if it is open source, then you could do that there. But I'm simply going to click Create Repository, and that is going to set things up. And here we are. So this here is our repo. You can see we have a few areas of interest. The first one is going to be this section here where we have our git ignore file. So this little window here is basically going to be our file explorer. Okay, this is going to contain all of our files and folders that we can navigate through as if it was a file explorer on our desktop. And then down here is basically a preview of the README file. So if we had a README file, this is where all the information would be listed out. Maybe if it was a public project, you'd be introducing people to the project and how to utilize it. And let's actually have a look at the git ignore file just to see what it contains, because right now this is the only thing in our repo. So I'm going to click it, and this is what we are going to see right here. So this here is basically listing out all the different directories and file types that we are going to exclude in the commit. You can see here the library folder, the temp file, the obj, the build, the builds, logs, etc. All of these folders which are specific to caching information and user preferences are not going to be included with the commits because other people might have different preferences set up. They might have their own library folder that, would have to be regenerated if we are modifying it so much. And generally, we are leaving out everything that is user specific, okay, like user settings, because if you have a layout of your editor and someone then pulls your changes, they don't want their editor all of a sudden mixed up and confusing, okay? So that is what the git ignore here also does, as well as a bunch of file types that it is leaving, as you can see here. And you can also go ahead and add in your own if you wish. Now to do this, we can simply go to the top right corner and click on this little pen icon, which will edit the file. We can modify them here, and then we can actually apply those changes by committing them here, okay? But I'm not going to do any of that because we aren't actually going to be modifying our project here inside of GitHub. Now, if I just click on my first Unity project, that'll bring us back to our main screen here. And the number one question you're probably thinking is, okay, we've set this up, now how do I actually add my existing Unity project to this, or how do I create a new Unity project to utilize this? And then how do I apply those changes? How do I pull those changes? Because right now we are just on a website here. Now we can click on the green code button and download that as a zip, but again, that's only a bit of the issue solved. And how is this any different than a Google Drive or a USB stick, for example? Well, in the next lesson, we are going to be looking at downloading a piece of software called GitHub Desktop, which is basically an application that interfaces with the GitHub website here. Okay, so thanks for watching, and I'll see you all then. Hey everyone, in this lesson, we are going to be looking at installing GitHub Desktop. Now, what this is basically a piece of software that is going to be the interface between our local project on our computer and our GitHub repository here on the GitHub website. So basically what GitHub Desktop does is it is going to basically create the repo on our local device on our computer, and then whenever we make any changes to those files and whenever we add any more files, it is going to be able to recognize those. We can then commit those files, have a little message, and then push those changes to the repo. Likewise, if changes have been made to the repo, we can then pull those changes and have them be applied to our local project, okay? And this basically is an alternative to the typical way of utilizing Git, which is by using a command prompt, which as a beginner user, it is fairly overwhelming. So this nice visual layout and visual way of interacting with your files and your different branches of your repo is a much nicer experience. So what we're going to do is, again, go to the GitHub desktop webpage, which is going to be at github.com/apps/desktop. Okay, and we are then going to click on the download now button. We can then choose our operating system, so I'm going to click download for Windows, and that will begin the process. Okay, so once that is done, we can then open up the setup.exe file. Okay, and once you have gone through the installation process, you should then be here inside of your GitHub desktop software. Now, I've already got some repos assigned to it, but we'll go through the process of actually connecting our account right now. So what I'm going to do is go up to where we have File, and then go down to Options, and then in Options here, we are going to go to Accounts, and then click on Sign into GitHub.com. We'll click Continue with a browser, and here it is going to take us to a sign-in page where we basically then want to select the account we want to use. So I'll click Continue on my new account here, and then click Authorize Desktop. And there we go. So now we can click Open GitHub Desktop, that will bring us back, and we should then be connected. Now to make sure, we can go back to the options and see in fact that we are connected here with our GitHub account. Now we can do what is known as cloning a repo, which basically means we are going to get the repository for our repo that we just created, and then clone that, which basically means download it and put it on our local machine here. So whenever we make changes to those specific files at that directory, those changes can then be committed. So to do this, we are going to go up to the top left corner here where we have our repository button, and we are then going to go over to the Add dropdown and select Clone Repository. Now inside of here, you should be able to click on github.com and see all of the repositories that are linked to your account. Now here we have that My First Unity Project repo, which we are going to select, and then we can choose a local path. This is where the files are going to be stored on our computer. If you want, I'd recommend creating a GitHub subdirectory to store all of your GitHub projects, or if you want them on a different drive, make sure to switch that over right now. So once it is done, we can simply click on Clone, and there we go. So now here we are inside of our repo. Now, to make sure that everything has been set up correctly, what I'm going to do is actually go over to that folder where we have everything set up right here. So as you can see, I am in my GitHub subdirectory, then the My First Unity Project folder. And in here, if you remember, the only file we have in our repo at the moment is that .gitignore. Okay, and if we open that up, that's going to be the exact same file as before that we saw inside of GitHub. So now any files that we add or modify inside of this My First Unity Project folder, all of those files will be tracked, their changes will be recognized, and when a change has been made, it will basically appear here, and then we can commit and then push those changes. So in the next lesson, we are going to be looking at how we can actually link a Unity project to the repo and start submitting those changes. So thanks for watching, and I'll see you all then. Alright, so let's have a look at how we can basically apply or add our existing or a new Unity project to our repo. So if you have an existing Unity project, simply open it up here on screen inside of your file explorer. Now we want to be inside of the project file. You can see here, I'm inside of the project folder where we have our assets, library, logs, etc., all of that. Now, if you want to use a new Unity project, then simply just open up the Unity Hub and create a new project, and then navigate over to those project files. Now, the next step is going to be opening up your local cloned repo folder. So this is basically where our repo is being stored on our computer. You can see here, all we've got is the gitignore file. And then what we're going to do is simply select all of our files and folders relating to our Unity project. Now, do make sure that these are the folders inside of your main project folder, okay? Because this, my first Unity project here on the left-hand side, this is going to act as our project folder now. So we simply then want to just copy these over like so. And there we go. So now we have our Unity project copied over to our GitHub cloned repo folder. You can still see we have the .gitignore inside of our project files here. Now, what we're going to do is we are going to go back to GitHub Desktop, and you're going to notice something has changed. And that is basically we now have a large list of files appearing here on the left-hand side. And these are all the files that the GitHub Desktop has noticed that have been changed, added, or deleted. Okay, you can see here we have a little green icon, which basically means this is a new file that has been added. We can see the file name and the directory on the left-hand side. And if we click on these files, you can actually see all of the data that the file contains. So if we go down here to where we perhaps have our input manager asset, you can see this is basically going to be that input manager asset that we would have in Unity. Now, we're going to get into a bit more detail about how working with scripts and all of that works with GitHub, as we can then see specifically what lines of code have been changed. But you can see here, everything in green is essentially what has been added or what is new to the file, which is pretty much everything for every file. And you'll also notice that we are not having our library folders or our OBJ folders here, and that is because that gitignore is filtering out everything that we do not need, or that we do not want to be added to our repo. So only the folders and files that are important will be included. So what we then want to do is commit these changes. So to do this, we're going to go down to the bottom left corner where we can enter in a little summary for what this is. So basically, when you're doing commits, it's a great idea to actually include information about what changes you are making, what files you have added, what things you are doing. Now, since this is our first commit where we are basically just adding our project, I am just going to say added project to repo, like so. Now, if you have any further information, you can add that to the description down here, but I'm simply going to click on the commit to main button at the bottom. Now, those changes have been committed, but if we go up to our GitHub repo here and refresh, you'll notice that, well, nothing has changed. And that is because even though we have committed the changes, we have not pushed them to the repo, okay? They have only been committed on our computer. To push them, we want to go to the top of our screen here, and you'll see there is a push origin button with a little 1, meaning there is one commit to push. We are going to click on that, and that is going to begin the process of uploading those files to the repo. Now, if we go back to the repo and refresh, what you'll notice is that our project has all of a sudden appeared here on the GitHub servers. So we basically just have our Unity project listed out here. We can go through all of the different folders, look at all these different files here as we could. So now the next step is going to be looking at what happens when we make some changes to the Unity project. What happens when we add a file? What happens when we create a new script, add a new material, modify a material, for example? We can then look at applying those changes and also perhaps even choosing not to commit certain files. So that is what we're going to be looking at in the next lesson. Welcome back, everyone. In this lesson, we are going to be looking at making changes inside of our project and then seeing those changes appear inside of GitHub Desktop, and we'll then go over exactly what those changes show, if we want to choose to leave something out of a commit for some reason, as well as some other things as well. So here we are inside of our project, and I'm going to start by just creating, let's just say, a script. So we can create a new C# script here. We'll just call this one player, for example. We might then want to add in a cube to our player scene right here. And then let's just simply attach this script and provide some basic movement code. Okay, so we'll open up this script inside of Visual Studio and just write something simple. Okay, and there we go. So just some basic movement code. Now we can hop back inside the editor, apply speed to the player here, press play, and just make sure it works. And as you can see, there we go. So now what we can do is save this, and if we go back to GitHub Desktop, what you'll notice is that on the left-hand side, we have a few things appearing here, okay? So these are the files that have been changed, okay? So you can see we have a brand new player .cs script right here. And if I select it, you'll see we have our code that we just wrote, and every line is green, meaning every line here is new. You can see by it having the plus icon on the left-hand side. Also, the player changed file here has a green plus, meaning it is new, whereas the sample scene down here, since we already included the scene inside of the project, that is not new. Rather, if we hover over, you'll see it is modified, okay? Now, let's just go ahead and, just for an example case, let's go ahead back to the project and delete a file. So this README that comes with the URP template, we can simply delete that. And then if we go into GitHub Desktop, you'll see we have a new file here. We have the readme.asset file, and if we click on it, you'll see everything is red, and that means it is basically removed. And if we hover over the red icon here, you can see it is deleted. So Git will keep track of files you have added, files you have modified, and files that also have been removed. Because if you, for example, want to delete something off the repo, that file also needs to be deleted on everyone else's computer, okay? Otherwise, you know, there might be errors occurring otherwise. So these are all the changes that we have made. So now what we can do is simply make a commit on this. So down here, we can go perhaps added player script. We can then commit that to the main thread and then push. And there we go. Now, if you also want to see a history of all the commits we have done, you can go to the top left corner, and where we have changes, we can switch over to history. And here we can actually have an in-depth look at all the different commits and pushes that have been occurred by all the different collaborators. So if we select the first one here, this is basically where we created the repo and added the git ignore file. The second one was when we added our Unity project. And the third one is the one we just done, which is where we added the new player script. And we can even see all of the changes that have been made. So if there is an issue and you want to, backtrack to see what it was exactly, you can do that right here. Now let's look at what happens if we modify our player script and see what that looks like. So I'm just going to open up our player script here. Let's perhaps delete the normalized here at the end. And we might also add in a debug call here. So debug log moving, for example, okay, just to show that we are adding and modifying the code. So now, if we go back to Unity, everything compiles, and if we open up our GitHub Desktop here, you can see we have one change detected, which is that player script, and this is what it looks like. So what you'll notice is that we have one line removed, and that is basically the line that we modified. And instead, it will then show us the line it has added, okay? So basically, it's not replacing a bit of the text, rather it will replace an entire line with a new one with the modification in place, okay? And then, of course, we have the additional lines down here for the debug log message. Now, let's just say we have written this, we go through our commit messages here, or our files that have been changed, and we go, okay, before I commit this, I kind of want to revert this change. I don't want this change to have happened. How can we basically revert that? So what we can do is right click on the change we have made in the left side panel and simply click on discard changes. And what this is going to do is it's going to have a pop-up appear. And basically when we click discard changes, that is going to revert all the changes that have been made to that file. So if we open up our script now, you'll notice that the debug log message is no longer here and the input line has been changed to have the normalized added back. Okay, so basically, if you're going through, you realize that you accidentally changed something that you shouldn't have, maybe you're modifying a file that you know somebody else is working on, then you can simply revert the commit change that way, rather than having to go through and change line by line to how it was before, as even if you do that, there may still be some metadata that gets transferred over, and it can cause issues if two people are working on the same file at once, they combine, and they conflict in some way. Although there are ways to merge script files. So if two people are working on the same script file at the same time, there are ways to merge them together, although it can be a bit messy, but we will be looking at those in the future as well. So that is a look at how we can basically make changes inside of Unity and also how we can revert those changes.